As I have mentioned several times, today is going to be quite interesting. We have been working on dealing with the minimizing problem from the beginning, and then today we're gonna try to more or less sort of finish the basic points, basic but very important points about the regularity of the minimizers, meaning that we can sort of have a big pictures of things, right? Because we have got existent result and now we just need to prove regularity results. And this is by no means trivial. It's not easy. I um, there's some other ways, but I don't think that anyway it's gonna be simple. So the problem is that we fix the two endpoints, right? You any admissible curve you fix at a equals to y, at b equals to z, and you are considering all sort of like absolutely continuous curve connecting y and z. A priori, I mean, we have no ideas whether they are smooth or nice enough. But eventually, it turns out that we can prove that, again, the theorem says that on the left, the theorem says that if gamma is a minimizer, then you would imply that gamma is ck, and gamma surely solves the Euler Lagrange equation. That's going to be the theorem we try to prove today. Yeah, and there's some steps that I'm going to be a bit sketchy because it's just a little bit sketchy, not too much. So that's the setup. The admissible set here is absolutely continuous curves. And again, our setting is that L is nice enough. The assumption L is nice enough, that's not a big deal. You can always put such assumptions. Uh, the key assumptions that we need is that L is superlinear and locally uniformly convex, okay? So or some way. And again, there are some parts that I'm being sketchy in the notes and also in the lecture because I want to focus on the key points. Do interrupt me or do let me know if there are concerns or point that you want to discuss. Okay, so the first step is simple, I would say that first, again, so we divide into few steps, right? Few steps. So first step is simple because we just use the fact that, the Lagrangian is superlinear, hence it dominate any linear growth functions. And in particular, you can see that, you have Lxv is greater than equals to v minus a big constant c, and this allows you to conclude that uh, the you know you can think of this as a length of the curve, right? It's less than equals to a constant. Okay, again, I should have said that gamma here is a minimizer so that we are not dealing with a random curve. Okay, so you have that the velocity, the integral of the velocity is bounded, and of course, you have gamma exists almost everywhere. So no matter what, you just need to find a point. So just find one point, maybe, yeah, t naught in AB, so that you have that gamma dot of t naught exists because it exists almost everywhere. So at that point, and then you can see that gamma dot of t naught is less than c, right? You can write exactly c over b minus I, but this is denoted by c again. My constants change from inequalities to inequalities and line by line. Okay, so you have the existence of one point at which its velocity is bounded, and that's enough for us. Okay, and then you can see that okay, so the second point is a little bit more involved. So I would say that second point, so it's more involved and complicated in the way But let me explain that it's actually quite interesting. This is often used in OD theory or in any kind of you know implicit or inverse mapping theorem. So what you want to show is that the first thing first. So the first point is that you want to show that near T naught everything is nice, and this is not too hard to show. I mean, um, what we are using here is just the fact that the integral, you have the integral um, how should I put it? The integral from a to b of gamma dot s ds is less than c, right? So in particular, you can throw away all pieces. This implies that for okay, so this is t naught. This is a b. If you take any small interval around it, just t naught minus delta to t naught plus delta, then what you have here is that for any say t within t naught minus delta to t naught plus delta, you can imply that the absolute value of integral from t naught to t of gamma dot s ds is less than equals to c, right? Uh, okay, and then hold on a second. I think that I wanna. Uh, no, I mean no, I mean there's an easier way to there's an easier way to do this. So let me delete this part. There's no need to use this. So from here, and what you already have is that sorry, I mean I want to say something simpler. I don't want to use big mechanism here. You have gamma dot of t naught exists, and you have gamma dot of t naught is bounded by a constant. Okay. So there are different ways to handle this, but what you can use is just the Taylor expansion, right? So what you can use here is that you have that gamma t minus gamma t naught equals to gamma dot of t naught times t minus t naught plus some omega of t minus t naught multiply with the length of t minus t naught. Okay. And then because omega is just a modulus of continuity, right, which goes to zero as t goes to t naught. So by changing the constant c to 2c, you can see that for t minus t naught less than delta, you can have that gamma t minus gamma t naught is less than equals to 2c times t minus t naught, and this is written as c times t minus t naught. Okay, so I'm changing the constant every time, but what I meant is that nearby you have gamma t minus gamma t naught is less than c times t minus t naught, so that's easier way to do it. um, Okay, now, so that's easy. The second part, the second box here is much harder uh, in general, but it represents some of the sort of key point in either control theory or in ODEs or stuff like that. What you want is that, let me highlight it here. So we just explained the first box, which is easy. The second box is really interesting, and it represents one of the key point we need in the proof. So let me really emphasize this. This is one of the key point. One of the key points that we need. And what we meant here is essentially, let me say it in word. You start at a point, gamma t naught, and you are allowed to go with any given velocity. Okay, so you can go with any chosen velocity, in along any directions. Okay, so what I'm saying here is that velocity v can be anything in the ball of center 0 radius 2c. So you can, you can vary your velocity at that given point. And what we are saying is that by doing so, we can reach to any point nearby. So that's sort of a controllability problem that essentially says that, with given velocity bounded by something, then you can go to certain directions and anywhere you need, and that's exactly that. So if you goes to up to time s, then you can reach to a ball of center gamma t naught radius c times s. Okay, so that's essentially it. So um, here, the projection map p essentially is the projection maps that project xv to x. Okay. So you see that I'm projecting from the R to N to R. Maybe I should have said P is mapping from Rn cross Rn to R, and it projects to just the position X. Okay. Okay. So that's the theorem, and then we need to prove this carefully. However, as I said, this is already occurring at in um, many literature. So I'm just gonna do it quickly because this was already explained and done many times. So you can check me on this, but I mean, so what I'm recording here is that I take phi t of L. So starting at x and v, I recorded it as the part gamma, but I'm being careful. So I put gamma depending on x and v, right? So gamma t is going up to the time t, and depending on the x and v, I mean, I'm writing it in a fancy way. You can see that this is essentially nothing but gamma t, gamma dot t, right? That's exactly the map, but I'm just trying to be careful that I recorded the dependence on x and v. And you can see that, of course, if you take time equal to 0, then you have exactly the x and v, right? At x and v, then just x and v at 0. Okay. Now, the map capital gamma is something new. Capital gamma records the difference, right? Divided by time t, because I would want gamma at time t to reach any point around gamma t naught with the ball of center c radius, ball of center gamma t naught radius ct, right? So in order to record that, I want to take, I want to normalize thing. Maybe let me write down here. So we want to have that gamma txv to be anywhere in the ball of center gamma 0 radius ct. Okay, let's assume that t is positive now. So this is equivalent to the fact that I want gamma t minus gamma 0 over t to be anywhere in the ball of center 0 radius c, right? So that's still a controllability problem, allows me to reach any point, but I'm just normalizing it. Again, it's just a certain technique. I'm normalizing things and put things in good order so that I can apply the either implicit or inverse function theorem. So that's what I'm doing. I'm taking exactly that normalization, and by using the fundamental theorem of calculus, I can rewrite that fraction into the integral. Hopefully I'm not missing any constant. I think it's correct. So it's just the integral from 0 to 1 of del gamma over del t of st xv ds. Okay. And you see what I'm doing. Now, in order to show that gamma can reach any point in a small ball, what I'm trying to do is that I'm trying to phrase things at a inverse function theorem, that gamma, essentially satisfying the properties of the inverse function theorem, at which I have um, the gradient is a matrix that is invertible, right? Then I can just use it, and that's exactly what I'm doing. And you can see that by calculations I can differentiate gamma in direction t and v, and naturally you differentiate in t, you have if you do it careful, you see that you have uh, the del square gamma over del t times s ds, because there's a s dependent in st. So when I differentiate, I have s pops out. And when I differentiate in v, then just that. Okay. Um, and now, in order to record the whole thing with time and space, and I need to define gamma tilde. And gamma tilde now also concerns with time. So I let gamma tilde txv to be t, and gamma t and gamma of txv. Okay, so in a nutshell, you can think that gamma tilde is a map from Rn plus 1 to Rn plus 1, because I also put time there. Okay, and you can try to find the gradient of gamma tilde, and the gradient here has to be in t and v, right? Okay. uh, Maybe let me write in a better way. D of gamma tilde is d in t and v of gamma tilde. So you just differentiate it in x and v. If you differentiate the first lot, which is t, if you differentiate in t, then you have differentiate t in t, you have 1. Differentiate t in x, you have 0. Then for the next slot, when you differentiate gamma, you differentiate gamma in t, you have del gamma over del t, no big deal. And then you differentiate gamma in v, you have del gamma over del v at 0 xv. Okay. And there's one tiny but important thing to notice about del gamma over del v at 0 xv. What is this term? Again, I need to check that gamma is nice, C1 and stuff like that. I'm skipping that. As I said, I'm just doing a sketch here for you. But you see that when t is 0, then gamma, when t is 0, then you have gamma of 0 xv is nothing but just v, right? So it's the identity. So when you find del gamma over del v, then what you get here is this one is nothing but the identity matrix In, right? In here is the identity matrix of size n. So when you differentiate that, you have this matrix, and you can see that the determinant of d gamma is nothing but 1. So that means that gamma tilde is invertible, right? And when it's invertible, that means that it maps from an open set to an open set, and that open set allows you to conclude that you have that open set allows you to conclude that you know you have an open ball near the center. That means that you can reach any direction. Okay, so this is a tricky thing, but it has been done many times in, again, control theory or ODEs in many directions. And this is really beautiful. The way we use either, you can do it either ways. You can use it either the implicit or inverse function theorems. Either one's gonna work. Okay, so that's that. And as I said, it's nice, and it's one of the key points that we need in doing in proving this result. And I'm using it right here in the fourth step. But before that, here's another point that I mentioned we needed to use last time. So the third step, let me just say it aloud. This different colors better. Third step is about sort of like using local theory of of Hammington Jacobi equation. I mentioned it in the last part of our class last time. Equations. This is by via characteristic method. So you see that this is one of the reasons why I meant that our proof is actually very complicated and quite involved, because it's related to various different parts of math, right? You know, it involves ODE, it involves controllability, it involves uh, local theory for Hammington-Jacobi equations. And what we are doing here for the moment is not very evident, but you can see that, you know, we just said earlier that for any velocity v here, we are able to reach to any given point. So just keep that in your mind. So so I need to, in a way, adapt that for this thing. So I'm just writing it down and I'll explain it in the next step. So for any velocity v, I let p to be just the dual of v, right? So p is dvl of gamma t naught v, so it's the dual of v. And I choose a function c of v in C2, so that it's it has bounded C2 norm, and the key point is that at the point gamma T naught, its gradient is P, okay? And then you, outside of a big ball, you cut it up so that it has compact support. So so the schematic picture is this, you know, uh, outside of a set, you just extend it so that it has compact support nicely. So this is minus r. This is r. Okay. Because gamma t naught it's a given is a given point to you, and velocity is just bounded, right? Velocity v is bounded by any c, and that means that p is also bounded by a given constant c. So what we are doing is that for any given gradient p, I chose a function CV correspondingly. Okay, maybe let me record it here. So we have point is gamma t naught and any velocity v for any v in the ball of center 0 radius 2c, and this point, you know, for such v, we correspond it to gamma t naught p, where p is the dual v, so p is dvl of gamma t naught v. Remember that this is correspond to v equals to dph of gamma t naught p. So it's just a dual, okay? So that's that. And for that thing, we can solve the Hammington-Jacobi equation in short time. That, you know, that we can solve it in short time for t between t naught minus delta 2 and t naught plus delta 2 for some delta 2. And you know, what we are doing here is that we put cv to be the initial data at time t naught, and we solve it. We can solve it for short time, and we have that uvc2. Okay, and again, technically it doesn't matter, you know. Okay, I should have said that technically we just need that uv is in C2 of b0r cross with the time from t naught minus delta to t naught plus delta 2. Okay, you know, everything is a local theory here, because we have everything is local. So again, you see that this is from a very distant part of what we are doing, right? I mean, we just quoted it and we use it later on, very later in the class. I will try to recall a bit of the method of characteristics. But what is really neat and important here is that, you know, is the fact that we can, you know, bring things together. And believe me, it would be great. I mean, there's some ways to avoid the steps of using characteristics. It would be great if we can come up with a very systematical way to do this without using this local part, but it does play a very important role here. So remember this in your mind. Who knows, you might run into this thing later on when you encounter very complicated problems. You have to bring parts together, and this is a part that's really neat in my opinion. Okay, so now we're gonna bring things together here and now you see that what I'm doing. And again, so this is the step that so step 4 is that we're gonna bring steps 2 and 3 together in a very neat way. um, okay, so how do I bring them together? Okay, on the one hand, I know what is gamma t naught, right? So it's just a fixed point. So I drew the time here at t naught is gamma t naught, just a fixed point in Rn somewhere. And I consider up to time t naught plus delta 2. It has to be somewhere here, right? So, okay, maybe let me also draw a picture here. So in Rn only, I know that this is gamma t naught, okay? And I go to up to times delta 2, so gamma t naught plus delta 2. And we just showed earlier that gamma t naught plus delta 2 minus gamma t naught is going to be less than some constant times delta 2, right? So that constant is given to us. Okay, fine. But what is really interesting here is that it tells us that, you see that gamma t naught plus delta 2 is within a ball of center gamma t naught, radius c delta 2, right? So this is essentially reachable if we use the earlier part, here in oh, I'm sorry, yeah, in step 2, right? What in step 2 here we are saying that you know if we run our Lagrangian flow, it we can reach to any point within the ball of radius c times length of s, right? And you see that this point gamma t naught plus delta 2 is reachable. So reachable here means that I can choose a vector v so that I can reach this point through my Lagrangian flow. Okay. Sometimes I would forget L. So I mean, so by abuse of notion, let's just write phi t L equals to phi t by abuse of notion, because I would forget many times. Um, so we see that gamma t naught plus delta 2 is reachable, so it should equals to eta t naught plus delta 2 for some given velocity v in b0 to c. Right? Again, c here can be chosen very big so that I can reach it. So at the end of the day, the main point here is that the red curve is gamma. The red curve is gamma, but it's also doable by choosing a part eta in our way, right? Eta is something, I don't know what is eta. So eta is something that eta is chosen with the given velocity v. So what it tells me is that I can go with some given velocity v somewhere. I don't know what is the velocity v. I just know that it's bounded by 2c. So that if I start the flow, the Lagrangian flow with the velocity v, then I can reach to the point here, right? So with that velocity v, then I can reach to the same endpoint, gamma t naught plus delta 2. Okay, so that's a step 2 that we are using. Okay, so let me tell you right away then. So then we use step 3 to show that that gamma has to be eta. Okay. So what I'm gonna use, why is it good? This is good because then we can see that a gamma is a minimizer that we start with, right? But eta is the flow of the Lagrangian flow, and eta is nice, right? It's ck. So hence, if they agree here, then we're gonna be able to conclude that gamma is ck locally and then hence globally. So that's the idea. Okay. And why so? Because you can see that here we encounter exactly a minimizing problem here, right? Because we have the two same endpoints now, gamma t naught and gamma t naught plus delta 2. So exactly two same endpoint. So that's exactly what I wrote down here. We have the same endpoints. So now how do we handle this thing? Okay. So on the one hand, hold on. Okay. Yeah, my notation isn't great here. I'm sorry. Let me change the eta to be alpha. I so that I'm not confusing you guys. So alpha is the curve that I'm able to use to connect the two, because I don't want to confuse you guys because I'm using eta as a generic curves that having the two same endpoints. So for eta is a generic curve. So this eta is a generic curve here. Then for any eta is a generic curve. How do we compute? I'm just using UV. That's exactly the local C2 solution to my Hammington-Jacobi equation, right? So I'm first writing down what's the value of UV evaluated at the two endpoints. What's the difference? And remember that UV is C2, and because it's C2, then you can use the chain rule and differentiation rule as usual, right? So as UV is C2, we can differentiate UV normally. Okay. Let me also correct this. I'm writing shouldn't be eta, should be alpha. Oops. Okay. So UV is that. So it's C2, so I can differentiate normally. So I'm just using exactly the chain rule here. I'm just using the chain rule and the fundamental theorem of calculus. I differentiate in T. I have either UT or either DUV dot with eta dot S. I'm missing the V here. It should be UTV everywhere. Okay. And then you see that this trick is being used again, as I mentioned, every lecture up to now, right? It's again the inequality in the Lagrange transform, the duality inequality. So duv dot with eta s is going to be less than equals to h of eta s duv plus l of eta s eta dot s. So that's same inequality we have been using all the times, and also UTV. Okay, so this is just being kept, and again I'm missing v here. Okay. And clearly this allows us to conclude. So remember that maybe a better color. This combining with this gives you 0, right? Because UT is a local solution to our Hammington-Jacobi equation, so you can omit that part. Again, this is a very simple trick, but one of the most important trick in doing Hammington in dynamics and with KM theory. So then I can omit that part, and that allows us to conclude that if I compute UT of eta uh, at t naught plus delta 2 minus uv at eta t naught, then the difference is going to be less than equals to the integral of the Lagrangian. So this is going to be less than the action functional, right? So you see that what we can conclude is exactly that the action functional I of eta is going to be always greater than equals to uv of eta t naught plus delta 2 t naught plus delta 2 minus uv of eta t naught t naught. Okay, so this is exactly action function. So it's beautiful, right? You know, it's exactly telling us that, hey, we can control the action functional by using solution to Hammington-Jacobi equations. It gives us exactly a lower bound. Moreover, you can see that this lower bound, the inequality becomes equality when, right? So, um, so you have a lower bound, and you have that equality happens when, right? When, you know, you can trace back and you see that, hey, I'm using exactly the Lagrange transform inequality here. So for equality to happen, it's exactly the equality of the Lagrange transform. You know, it's so neat, right? It just comes exactly at the right place. Okay, so equality happens exactly when you have that eta dot s is equals to dph, right, of eta s duv of eta s, right? Exactly when that is the case. Nothing more, nothing less. Okay. So you see that that's exactly what I wrote here. So on the other hand, you can see that if I'm choosing alpha, so again, earlier I was making a mistake of saying eta to be alpha. Alpha is the part that is the specific part that we choose so that we reach at, you know, of the Lagrangian flow, so that we start at the same point with gamma and end with the same point with gamma from t naught to t naught plus delta 2. Okay, so you see that alpha satisfy alpha dot, you know, is x dot, right? And we already did the equivalence between Hamiltonian and Lagrangian viewpoint. So you see alpha dot is x dot, and that's exactly satisfying the Hamiltonian system, right? So it's exactly dph. So that's exactly when you have equality holds. Okay. Okay, so you have equality holds for this part alpha. This part alpha here. Okay, alpha is a chosen part first from the controllability viewpoint for some given vector v. I don't know what, but you know, I know that there exists at least one vector v so that I can reach to that endpoint. And you know, and because we have equality, so equality happens, meaning that I have uv evaluating the difference should equals to exactly the action functional, right? So so we see that that you know, I alpha is exactly the minimum value of I eta for all such eta with the two endpoints, and moreover alpha is the only minimizer, right? Why is it the only minimizer? Well, it is the only minimizers because you have the ODE eta dot is equals to dph of eta s duv of eta ss. Okay, so that is an ODE, and you have you know, you have that at, okay, here when I say equality happens at this point, and you can see that I should have said one more thing, that I have eta at t naught is exactly gamma t naught, right? So I have exactly just the starting point is fixed, right? And when my starting point is fixed, then the minimizer and the equality happens if and only if eta is alpha, right? So what is really important is that not only I can conclude that I alpha is the minimizer, but also that alpha is the only minimizer for us, not just, that again, I don't, okay, maybe a remark. So here, what is really important is that remark. So what we have is that locally, once everything is nice and we have existence and uniqueness of a local minimizer. Okay. I don't claim anything about uniqueness of a global minimizer for us from A to B, right? That is a tricky problem. Uh, but what is amazing is that we use control viewpoint, that we can reach any point through a vector v here. So if you choose the correct vector v, correct velocity, then you can reach to the end point, and that gives you the particle alpha. And we just show that alpha is the minimizer. So alpha is the minimizer. But moreover, it's really important that through the duality inequality, we have that alpha is the only minimizer. And once alpha is the only minimizer, then this allows us to conclude that um, eta equals to alpha on the interval from, say, t naught to t naught plus delta 2. Okay, so this is remarkable. So, oh, gamma, I'm sorry, not alpha. Somehow I'm quite bad with notions today. So when gamma equals to alpha on t naught to t naught plus delta 2, then clearly this allows us to conclude that at least locally, you can see that again. I'll remind you what is alpha, but at least locally you can see that gamma is ck on the interval t naught and t naught plus delta 2. Okay. So before concluding step 6, let me just remind not remind, that's not good. So just a quick recap for us about the Lagrangian flow, right? So VTL of xv is nothing but just gamma dot of t. Earlier I write, or sometimes you can write, see that I wrote it gamma t xv just to denote that it depending on xv. Okay, t of xv. Okay, but what is the point here, that you have gamma 0 equal to x, gamma dot of 0 equals to v, and you have it satisfying the Euler Lagrange equation, right? So d over dt of dv l of gamma dot t equals to dx l of gamma dot t for t in R. Okay, so what you can see that this is just a normal system of ODEs, right? And it's a normal system of ODEs, and that the solution is as smooth as the Lagrangian. So clearly what you can see here is that if you have this Euler Lagrange flow, then you do see that phi t of L is ck in t. Okay, so that's just a normal ODE theory. I'm not using anything more than that. Okay, so I have surely gamma ck on the interval from t naught to t naught plus delta 2. What is also remarkable here is that once I have gamma equals to alpha in a small interval, then I can conclude that actually gamma equals to alpha if you extend it to the whole interval AB. So here by this I mean that meaning that gamma equals to projection of P on phi TL of XV for all T in the interval AB. Okay. And surely then I can conclude that gamma is CK. So why can I say that from the fact that gamma equals to alpha locally to gamma equals to alpha globally? Can some of you tell me, just to finish our discussion for the class today? Why could I do so? Yeah, maybe the question is that, we surely have that gamma equals to alpha locally. So how do we conclude that gamma equals to alpha? No, on the whole interval AB. What do you think? Can some you give me a just a piece of discussion? Again, what we are doing here, as I said, I mean, this is probably known, but it's only written down in the clearest form recently in the last 20 years or something like that. No, I mean, surely that we have that it's CK and nice in a small interval, right? Because we are using the local theory. Yeah, I'm just curious. Why can you conclude that you have it's global on the whole interval AB? Again, I mean, the Lagrangian flow is defined on even on the whole R, right?
Can you restart the flow at T naught plus delta 2 and then choose a V starting from there again and continuing locally?
Yeah, absolutely. Yeah, because you can see here, I'm actually cheating a little bit here. Well, not cheating, I didn't mention it. What you said is correct, right? Absolutely correct, because you can see that the Hammington Jacobi equation can be solved back and forth around the point T naught, right? So you can go back and also forth. So absolutely that, actually here, not only that we have gamma equals to alpha on the interval from T naught to T naught plus delta 2, but in fact you have it's from T naught minus delta 2 to T naught plus delta 2, right? So the point is that you can go back and forth, and that's exactly what you said is exactly one way to prove it, because you see, okay, so we have T naught here, we have the agreement up to T naught minus delta 2 to T naught plus delta 2. Maybe this is A and B. So now you can start doing your problem at this point, right? So you can, go back and forth. The going back, it's actually very important, because it verifies that the past is the same like alpha, right? So, okay, let's say that maybe going back and forth here, maybe you have beta instead of alpha, but because beta agrees with alpha on the past, then it has to be alpha. Okay, it's beautiful. Okay, so the local theory for Hammington-Jacobi equation is that you can go back and forth in time, not just forward in time, but also backward in time in a tiny interval. And this is exactly, you see that we are using exactly the OD theory viewpoint here, right? Whenever we solve OD, we keep sort of extending it from, assuming that we stop and then extending it here. And this is exactly the point. Just we keep in our mind that this is going back and also going forth. So you have that this piece from here's alpha, and you extend it, this piece is beta, and you see that alpha has to be exactly beta, continuing. So it's the same, fit here. Okay, so we are done for the day. I hope that you see things clearly. Again, avoiding all the technicalities. In my opinion, you see the beauties and you enjoy it, and then you might forget. And later on, whenever you need it, maybe then you can pull it out of some corner of your brain, or then you remember that, it has already been sort of explained, or maybe been discussed in some part, and you can pull them back. uh, or maybe we never use it, who knows, right? But the whole theory that we have been doing in last 10 lectures up to today, it's quite striking in the sense that we built everything from the beginning. We have now been able to get existence and regularity of the minimizers, and we're gonna keep moving forward, starting to learn more of the properties of the minimizers. Now that we know that it's smooth enough, we try to learn more. And as I promised, we're gonna try to go really up to date. And you see that many parts are not yet well understood. There are many, many, many open questions, more than we can describe. Um, yeah, but that's pretty much it, and I hope that it's clear. Again, shoot me an email, or start a discussion if there's something unclear. And other than that, then thank you guys, stay safe and healthy, and I see you on Wednesday. Okay, thank
You too.
Bye. Thanks.